Okay, AP students, welcome to lesson 5 for our acid base chapter 14 unit. In this unit, in this video anyway, I'm gonna discuss the weak acid, weak base equilibrium. In other words, calculation of pH with weak bases, and then do a little bit of discussion on salts. We'll do some salt hydrolysis and figure out whether a salt is acidic, basic, or neutral, and then classify things based on their acidity all the way from acids to bases, including salts and weak acids and bases. And a little bit of chat at the end about some things that make things more acidic and so forth. So let's go ahead and get started. So this is just a list of those things that we're going to discuss. Okay. Yeah, I got it. So, yeah, we're gonna. Oh, I did want to talk. I forgot to mention that. I wanted to talk a little bit about the guided mini lab that we did with an unknown weak acid. You guys were supposed to determine the Ka. I wanted to go through a little bit of the math with that and explain how cool that really is. Also, identify the bases from their formulas and calculate the pH of some weak bases using some rice tables. And then identify the strength of acidic and basic salts and kind of classify whether something is acid or base from its formula and kind of how it behaves. But anyway, and then the last thing we'll talk about role of oxides and acidity. But let's go ahead and get started. Let's talk about the lab. So in the lab, you guys were given or you selected an unknown. From my students, it was A1 through A5, and they wrote down which one they had. And they went through a process of titrating it with phenolphthalein, hopefully to a correct endpoint. And then what they did was, and I'm going to kind of graph this on here and talk as I go. But what we did is we added some unknown acid, a solid acid, to a beaker and diluted it with 50 milliliters of water. And then we took 25 milliliters out of it. So the titration that you were doing was just with half the amount of acid you started with. Doesn't really matter how much it was, but it matters in the end. So we added 25 milliliters of acid, and then we titrated the sodium hydroxide with it until we got to the end point, which it kind of up here, and then we stopped when we got to the end point. And that was however many milliliters of base. It doesn't really matter in this case. The concentration of the base didn't matter, provided that it was high enough or low enough that we actually got some good readings. We were able to add a certain number of milliliters. You know, if we added 1 milliliter, that wouldn't have been good. And if you had to add 300 milliliters, that wouldn't have been good. So it did kind of matter where it was, but we weren't using that to determine what the equivalence point was. Instead, what we did is this was when we added the 25 milliliters of our acid. Then what we did is poured 25 milliliters of acid back in there. So we added another 25 milliliters of acid. And more important than the milliliters of the acid is the number of moles of the acid. So we added half the moles of acid and then found the equivalence point. Then we added half the moles of the acid back in there. And what happened is this then trailed back halfway to what we call the half equivalence point. Yeah. And so at the half equivalence point, some really cool things happen. So, or really cool things are able to be found. So anyway, at the very beginning, all you really have is weak acid, which I'm going to call for this purpose HA. Just A minus will be our conjugate base, and HA, excuse me, is our weak acid. When you first start the titration, you can find your pH from your Ka value. You know, just do a little rice table, whatever the concentration was, figure out the pH. On some of these, it was anywhere from like 2.5 to 3.8 or so was the initial pH. Fine. Well, what you have initially is primarily weak acid only. And so what happens to the weak acid as you add hydroxides, if I write it up here, the HA, as you add hydroxide ions, it's going to pull off the hydrogen to make water, and you're going to be left with conjugate base. So when you get to the equivalence point, you will have added the same number of moles of hydroxide as you added, as you originally had of the moles of your weak acid, in this case, HA. What you end up with at the equivalence point is nothing but A minus. Well, There are some other things there because A minus is a weak base and it's going to go back to produce the acid. But essentially that's what you have in terms of the titration is you start with entirely weak acid and then you end up with entirely, for the most part, especially if X is negligible in our cases, you end up entirely with conjugate base. Well, at this half equivalence point, what you have is you have weak acid and the conjugate base in the same concentrations. And with that true, you can do some really kind of cool, well, you can figure out some things about the acid, let's say. So I'm going to erase this and kind of show it to you real quickly. But at that point, at that half equivalence point, if I were to write my Ka, excuse me, expression for the above equation, I would have my products divided by my reactants, right? What am I doing here? So my Ka essentially is, and this is not the right equation. My Ka, that's a totality. Let me rewrite it, sorry. The Ka for HA would have products of H plus and A minus, correct? Not the titration, but here. So I have my H plus concentration times my A minus concentration. I left out the water here, it's fine, it would be left out anyway, over HA. What I said at the half equivalence point was that these two things have the same concentration. Let's say they were both 1 molar. Well, 1 molar over 1 molar is going to cancel out, and this is gone. So this value is 1. And so what I'm left with is that my Ka essentially is equal to my H plus concentration. If that's true, and when you added your 25 milliliters back in, you drag down to that half equivalence point, the pH at that half equivalence point would equal the pKa, right? I mean, what we're doing up here at the top, if I rewrite this here, I had the Ka is equal to the H plus. Well, if I negative log this and I negative log this, same thing on both sides, I end up having the pH equal to the pKa. So if you can find your pH, which you guys were hopefully able to do when you added your 25 milliliters of acid back in, let it stabilize, you now know what your pH is at that point. If you knew that, you can actually solve for the Ka. So to solve for the Ka value, it is, well, hang on a second now. Let me get ahead of myself. If I want to know what the pH or what the hydrogen ion concentration is, having known the pH, it would be 10 to the negative pH value. Well, if I want to know the Ka value, it is equally 10 to the negative of the pKa, or in this case, the pH, because the pH and the pKa are the same. So that's interesting. You can solve for what your hydrogen ion concentration is at the half equivalence point, but it will be the same as your Ka expression. So this allows us to identify what those acids were, and hopefully you were able to do that in this lab. Pretty cool stuff, in my opinion. Now, this will lend or lead us to using an equation that we'll use actually more so in the next unit, but it is the pH equals the pKa plus log of the conjugate base over the original acid. And this is actually called the Henderson-Hasselbalch equation. And having been given either the Ka or perhaps the concentrations at whatever point you are, you could figure out what the pH is, or you could figure out what ratio of conjugate base to acid you have present. There's a lot of interesting things that you can do with this formula, but it makes it so titrations go very, very quickly. Titration calculations, that is. So you could technically use this instead of doing rice tables for everything. Now, I'm getting ahead of myself because that's in our next unit. But I did want to kind of bring you back and kind of show you what's going on there. I've got another video kind of explaining it, but it didn't go into that much detail. And perhaps that'll help you guys get through your guided mini lab. So the next thing I'm going to talk about are going to be bases. And so the hydroxides of group 1A and 2A are considered strong bases. Now, group 1A and heavier 2A hydroxides are going to be more soluble, but that doesn't really make any difference. The solid bases will also react as though they are strong bases as well. So if you see hydroxide in a base, for instance, in AOH, or even calcium hydroxide, which isn't all that soluble, or magnesium hydroxide, as in this Phillips-Malka magnesia, they are considered strong bases and will react appropriately to produce water and whatever that other ion is located in the base. So, and they have lots of effective uses. Now, weak bases, on the other hand, don't have hydroxide in them. They generally have an amine group in them. In other words, you're going to see ammonia, you're going to see methylamine, you're going to see ethylamine, and so forth. They have those amine groups on there, which has that lone pair of electrons, which makes them Lewis bases. They donate the pair of electrons to form coordinate covalent bonds. But all that nonsense aside, if you add water to each of these, they will produce hydroxides in solution, which makes them bases. And we're going to do a little bit of that. Now, when you do reactions of weak bases, to prove that they're basic, you actually have to add water to them in order for it to occur. So look in here, I've got, let's just skip the generic base and go and look at go and look at this one right here. You have ammonia, you have to add water to it in order to predict the hydroxide. But the ammonia will combine with one of the hydrogens, that lone pair will go with one of the hydrogens of the water to produce the ammonium ion and hydroxide solution. Hydroxides in solution. And so there's kind of what's going down at the bottom as well. If you look at the balanced equation, at least in terms of the molecules, Lewis dot structures. But that's what's occurring here. And so whenever you do a weak acid Rice table, you can just dissociate the H plus and the conjugate base. Whenever you do a weak base, though, you're going to have to make sure you add water to it to predict the conjugate acid and the release of those hydroxide ions. So we'll go through and do one together, but here are some of the KBs for the ones that we saw above. And a KB is done just like a KA, which is just like a KEQ, which is the same thing as KC, which is set up the same as KPs. They're all Ks are the same. The concentration of the products, the product of the concentration of the products raised to the power of their coefficients divided by the reactants, the same. So if I had a strong base like sodium hydroxide or whatever, and it said, and I wanted to calculate what the OH minus is, this is the concentration given here for sodium hydroxide. Sodium hydroxide is a strong base. So sodium hydroxide will go and produce 100% sodium ions and hydroxide ions in solution. So I know if this is 0.0100, what I'm going to get on the other side is the same amount of both of these. I'm going to end up getting 0.0100 molar hydroxide ions. And I'm not going to have any more sodium hydroxide once I put it in the water. The reason is because it's a strong soluble salt. It's a group 1 and it's a, whatever. But it is a strong base. And so it will dissociate entirely. So if you want to find what the hydroxide ion concentration is, it's the same as the concentration of the base. So it's just 0.0100 molar. If I wanted to find the H plus of this, there's a couple of different ways to do this. The easiest way to do it is your Kw equals the product of your hydrogen ion concentration as well as that of your hydroxide ion concentration. So you could say that it equals the Kw divided by your OH minus concentration. That would probably be a little bit faster than solving for the POH, subtracting from 14 and taking negative the 10 to the negative pH. However, this is a little bit faster. So I would just do this by 0.0100 and I would get my answer. And that's 10 to the negative 2. So it would be 10 to the negative 12. If I were solving for the pH of this, I could then take, this would be 1 times 10 to the minus 12. So I could take that hydrogen ion concentration, negative log it, and I would get a pH of, and I guess I haven't really, the 1 times 10 to the minus 14 is exact. So probably need some more sig figs here. Let's get rid of this and say it's 1.00 times, my times really, 10 to the negative 12. So this pH would actually be 12.000 because I've got 3 sig figs here, 3 sig figs here. I need 3 after the decimal place of my pH. But anyway, I could also solve for the POH, though they didn't ask for it. That would be 2. I'll show you the kind of worked out stuff here. But that using the KW is the fastest way to the H plus. You could certainly find the POH, subtract from 14, find the pH, which you would then have, and then find the hydrogen ion concentration by taking 10 to the negative pH. It would take a little bit longer. So weak bases, you're actually going to need a Rice table. You got to be careful if you end up solving for X in a base, in a weak base problem. Remember that X value is not the hydrogen ion concentration like it was in weak acids. It's going to be hydroxide. So you'll have to take negative log of your hydroxide and then of course subtract from 14 to find your pH. Often they'll be asking for the pH, not the pOH. So that extra step matters. So let's do an example. So calculate the hydroxide ion concentration, and it says the pH as well, for a 15 molar, that's kind of a lot, 15 molar ammonia solution. So what I'm going to do is I've set up my equation already for you, a balanced equation. I added water to the weak base, and I've got a Kb expression set up, leaving the water out, of course. And so what I've got here is 15.0 molar for my ammonia, and I have 0.0 for my ions. My water is a liquid and is the solvent here. And so what I'm going to do is I'm going to leave it out of the expression by just drawing lines down here. If you want to do minus X in there, that's fine, but it's not relevant. So I'm going to lose X amount of this. I'm going to gain X amount of this and gain X amount of this. At equilibrium, what I'm going to have is 15.0 minus X, X, and X. I've already written my Kb expression. I can't encourage you guys enough to please write your Kb expressions and your Ka expressions. It'll make a difference when we're setting stuff up later. KSPs, salt hydrolysis, these things, it'll matter that if you write them out. So you really need to write it out. But I've got it written out. So what I've got here is 1.8 times 10 to the minus 5 is going to equal X times X, which I'm going to go ahead and write X squared because both those are X, divided by 15.0 minus X. And I'm going to treat the X in the bottom as negligible. Cross multiply my 15 and I could solve for what my X is. What my X is my hydroxide ion concentration. So that would be the first answer to this question. After that, though, I'm going to have to take the negative log to find my pOH. I would have to take a negative log of this number here in order to solve for that. And then to find the pH, I'm going to have to take 14 minus whatever that value is for my pOH. I'll show you the work here, and you can pause if you need to write this down, as I went kind of quickly. Sorry about that. But yeah, so the X value ended up being 1.6 times 10 to the minus 2. So I took a negative log of that to find my pOH. To solve for my pH, I would just subtract that from 14, and I have the other part of my answer. I think these are great. They're really no different than doing weak acid problems. The most significant difference, of course, is at the end when you have to find pH from pOH. So let's go on to salts. So we did a little bit of this last year. If you took advanced chem with us last year or pre-AP chem, neutral salts are going to be salts that have parents that are both strong, or they could both be weak if they have the same Ka and Kb value. In other words, their strengths are the same. If their strengths are the same as the parents, by parents I mean the acid and base from which the salt was made, they'll be a neutral salt. So if I were to look at NaCl, the parents of NaCl are NaOH, which is contributing the sodium, and Cl comes from HCl. This is a strong base, and this is a strong acid. So those will form neutral salts. So the pH of that salt, if you take sodium chloride and you put it in water, the pH will stay 7, or whatever the pH of the water was initially. It essentially will stay the same. Acidic salts are different. So if you look at what it is made from, this is made from the weak base ammonia. So that's the NH4 comes from ammonia, which is a weak base, and the Cl comes from HCl, which is a strong acid. So this would be an acidic salt. That is a quick way to identify whether or not it is, in fact, an acidic or basic salt. It doesn't demonstrate why, though. So if you want to prove that something is an acidic salt or a basic salt, you actually have to take the weak part of the salt, which is what we're doing down here in the bottom, take the weak part of the salt in the NH4Cl case and add it to water. If you add it to water, you predict the products, you end up getting hydronium ions, which is good, and the weak base that you started with. So the conjugate base of the conjugate acid from the previous base. But anyway, you end up getting it like that. You could also write it as NH4 plus goes to NH3 and H plus. But I would always add water. I would add water to the ammonia and predict it. It'll make it better if you take the weak part and add water to solve for what these are. So basic salts, that was an acidic salt. But basic salts are going to have the anion from a weak acid. And when that conjugate base from the weak acid reacts with water, it actually produces hydroxide ions. that means that it is a basic salt. You can't say, oh, well, the strong parent is sodium hydroxide, which it is up here in the sodium acetate. This comes from NaOH, which is the strong base. And this comes from acetic acid, H3O2, which is a weak acid. So this is strong and this is weak. But you can't say that. I mean, if I ask you, or if your instructor asks you to prove that something is acidic, basic, or neutral, you're going to have to take the weak part of the salt, if there is one, add water to it, and predict the products, and demonstrate that it produces hydroxide ions if it's basic, and hydronium or hydrogen ions if it is in fact acidic. So, and we did this last year, but I know you guys have slept a few times between now and then. Anyway, so Ka, Kb, and Kw, this was something I talked about earlier in the notes, but you can find what that Ka is or what the Kb is for the conjugates by setting them equal to Kw. We'll assume that most of these, or if not all of these, are done at 25 degrees Celsius, so the Kw will be 1 times 10 to the minus 14. Up at the top, it's showing you kind of different Kw values. We'll actually use the one up at the top, or the one down from the top at 25 degrees C, which is 1 times 10 to the minus 14. I don't think we'll use any significant figures with that. We use the significant figures from the K or a Kb from the parent that we have originally. But to find out what it is for that salt, you may have to do a little calculation like this off to the side to find out what that Ka or Kb value is when you ionize the salt and try to calculate its pH. So let's do a little example of that. So calculate the pH of a 0.15 molar solution of sodium acetate. Well, what type of salt is sodium acetate? Acidic, basic, or neutral? Okay, I could use my parent thing to figure this out. Sodium comes from sodium hydroxide. That's a strong base, so this would be a basic salt. To prove it, though, I've got to take the weak part, which is going to be the acetate, and I'm going to add it to water and predict what happens as a result. So use the weakest part of the salt and water to write an equation. I've written the equation down here at the bottom. This you could just write up there in that blank, but it's the acetate plus water will yield the original acetic acid, the parent, and hydroxide ions. So I've set up a rice table here to solve for the pH. I've gone ahead and written over there what you would do to find the Kb. Remember that the Ka is, excuse me, look at me, the Ka. The Kw is going to equal your Ka times your Kb. And what I've done is taken my Ka over here and divided it. So the Ka for acetic acid is this 1.8 times 10 to the minus 5. You could then run that calculation and find out what the Kb is for the acetate anion. So it said that this was, what was the concentration? 0.15 molar. So what I'm going to do in here in this rice table is write 0.15 molar. I'll leave my water out, 0 and 0 to begin with. I'm going to lose X. I'm going to gain X. I'm going to gain X. And at equilibrium, I've got 0.15 minus X, X, and X. I would set up my Kb expression, you know, putting my acetic acid times hydroxide divided by my acetate, solve for X, and that X will be my hydroxide ion concentration. And so I'll show you the work here. It's down here at the bottom. Sorry, it's kind of massive. It's stuffed in there at the bottom. But I have set up my Ka expression right here. The Kb is what I solved for over there on the right. This is solving for the Kb over here was 5.6 times to the minus 10. I set it up in terms of X, and then I solved for X. And then I kind of in the background, I didn't show you how, but if I took the negative log of this number, I will get my POH. To find my pH, I just did 14 minus my POH, and that gave me my pH. So kind of left a couple steps out of there, but that's how you would end up getting to that point. So what if you were given a list of things? You have to be able to identify whether things are acids, bases, salts, weak acids, weak bases, whether they're strong acids, or all that stuff. And so here's kind of an example of that. So rank the following in order of most acidic to the least acidic. I mean, you guys can hit pause and try this on your own. That'd be great. You can come back and I'll show you. Why don't you try that? So let's assume that you gave it a shot. I would identify the strong ones first, right? That would be pretty easy. I've got sulfuric acid here, which definitely would be most acidic. That's a strong acid. And I see strontium hydroxide. It's a hydroxide, group 2A, so that's strong, SROH2. I could cross those two out, and I'd have the sides done, I guess, the most acidic and the least acidic. You could also probably figure out the middle pretty quickly. You would look for something that is neutral, something that had a parent that was a strong acid and a strong base. That would be NaCl. So NaCl would be your neutral salt kind of in the middle. Now, generally speaking, things that are salts are not going to be as acidic as as a weak acid or a weak base. So more towards the outside are going to be your weak acids. So a weak acid here would be HCN. And the weak base over here would be this, where was it? A methylamine, CH3, NH2. And then our salts in the center. And so our other salts were potassium acetate, which is a basic salt, KC2H3O2. I quit crossing things out. Look at me, I'm losing my mind. And then the last one would be the ammonium chloride, which would be your acidic salt. And that's how you would order them. Yes, you probably should go and find out what their Ka and Kb values are, calculate their pHs and all that stuff. But generally speaking, they'll be in this order: strong acids, then the weak acids, then your salts, acidic, basic, and then acidic, neutral, and then basic, then your weak base, and then and finally your strong base at the end. So here's kind of that thing again, but typed and pretty. Sorry, my messiness stuff. But that's kind of the order from most acidic to least acidic. So a couple of last minute things. We already talked about oxides and the numbers of oxygens earlier, but there is something, you can't produce acidic and basic solutions with certain chemicals or compounds. So calcium oxide, when it reacts with water, and you may remember this from our synthesis unit or not, but as you add water to it, it actually becomes calcium hydroxide, which is basic. So if you have a metal oxide, you will produce bases in water. If you have a strong base, in fact, if you have a non-metallic or a molecular compound like a gas, like CO2, and you add it to water, you actually produce H2CO3, which would be an acidic solution. Now it's a weak acid solution. The similar would happen with SO2, and you might remember that. But if you add things that are non-metallic or covalent in nature, they will actually produce acids in water. And there's the sulfur trioxide producing H2SO4 there on the bottom. Similar, not SO2, but SO3. The last thing to talk about is kind of an aside, but it works a lot, kind of the same way as oxygen or acid strength with oxygens. If you have a salt of a highly charged metal, so in other words, and we don't really do a lot of complex ion stuff in AP because it's been removed from College Board's curriculum. However, just a quick, and this is pretty easy to understand, if the center of this, and this complex ion, looking at this one up here, and I've got water molecules around the outside, but I have a highly charged metal in the center, what the highly charged metal does is it pulls on the molecules on the outside, and it leaves the hydrogens kind of stranded with very weak polar bonds. They're polar covalent bonds, but they're not nearly as weak as strong as they were before. And so that hydrogen is easier to dissociate. At least one hydrogen, sometimes multiples, but at least one hydrogen is pretty easy to dissociate. If you're given a comparison of one charged metal to another one, the point here is the one that has the highest charge is going to pull the most on those electrons in the bonds, making that attraction for the hydrogen weaker, and thereby allowing it to dissociate. And so this hydrogen will kind of pop off here, and you end up with an acidic solution. This doesn't make it like a strong acid solution, but by no means, but it will make, they will be stronger the higher charge of the metal. So guys, that completes our unit on acids and bases. We're going to revisit a lot of this in the next unit when we talk about acid-base equilibria and buffer systems. I'm looking forward to that. It'll be one of our most difficult units of the year, but students do typically very well on it because we go very, very slowly and show you how to do them. And this is an excellent intro into that next unit. Okay, see you guys next time.